and I think it's time to start. So my name is Ole Madsen, and I'm a professor here at the Department of Materials and Production. And I've been appointed to be the moderator of this event here. So my task is actually to introduce all of you to who the persons are here. And first of all, I'd like to introduce Emma, who's the main person here today, who will present his PhD thesis called Virtual Factories as Systemic Approach to Building Smart Factories. So I really look forward to your presentation here. You have been employed by the Department of Materials Production. You've done your PhD on the MATE program, and you've done that in collaboration with Vestas. So we'll hear from you in a moment. Then we also have the assessment committee, consisting of Professor Emeritus Ron Sanchez from Copenhagen Business School here in Denmark. But you're not in Denmark at the moment. You're far away in the morning in the US somewhere.
In Oregon, USA.
Okay, so it's morning on your side. So good morning to you, and welcome to this session.
Thank you.
The second member is Professor Peter Gorm Larsen from Aarhus University. So welcome to you. And finally, we have Anne-Louise Andersen here from Aalborg University. And I believe you're the chairman of the assessment committee.
Chairman, yes.
Chairwoman. We also have some supervisors. So we have Charles Møller, who's been your main supervisor, I believe. And we also have Arne Wilberg, who has co-supervised, being your co-supervisor. And we have Arne with us online. Yeah, and then finally, welcome to all of you for coming here for this session here. Before I'll leave the floor to you, let me just remind you of the rules that we have for these PhD sessions here. So what will happen is that Emma will present for 45 minutes. Then we'll have a small break. So those of you who will not stay here for the whole session will have time to do something else. Otherwise, the rest of us can stretch our legs. And then we return back here at 4 o'clock for the questioning round, where the assessment committee has time to ask questions. This will take maximum 2 hours. So one of my hard obligations will be to stop you if it runs beyond 2 hours. There will also be a chance to take questions from the audience. So if you have any questions, you should come to me in the break we have after Emma's presentation. And then we will schedule the questions you might have. Yeah, I think that's it from me now. So I will leave the floor to you, Emma, and I really look forward to your presentation. So enjoy.
Thank you very much. Welcome everyone. Today I will talk about my PhD journey. It took more than 3 years, so it will be a bit more, quick presentation about 3 years journey, what we faced, what we discovered, what we learned. So the content is simply, I will first talk about the introduction, the context of our research. Then we will go to some challenges and problems and research motivation. And then we will look at some objectives and questions we try to address during this research. Afterwards, shortly, the methodology. And if you are still alive, we will look at the results and hopefully have some fun videos about my work. And lastly, we will have some discussions, mainly try to look at what that means, this research means for the industry and academia. So, as Ole mentioned, this is a MATE project, Manufacturing Academy of Denmark, and I was hired by Aalborg University, and Vestas was named industry stakeholder. And the project developed between these 3 stakeholders called smart factories. So I also partially work with Inestec and collaborate between these main stakeholders during these 3 years. So we start with a frame. You see, this is not very traditional research. I did not come propose a research subject and get a grant for it, but there was already a research package with a framework. We call that some expectations. I put some of them here. As you can see, they asked me to focus factories, digitalization, digital infrastructure, the data there, and what kind of values we can capture from this data with solutions, means of digital technologies. The first phase in the main is the idea generation. Look at the industry, find a problem, define the objectives of a solution, and design a solution. And the second phase, the most important maybe, to prove the concept. It's not just the theoretical work. Develop a demo, put it in the industrial case, and evaluate it. And if it is still valuable, then it can be a prototype and maybe an actual solution in the industry in the long run. So of course, this proof of concepts, first two phases, iterative. We can go in the first time and find some issues, go back to the original idea or the solution or the objectives. So proof of criteria, since we try to solve an actual problems in the industry, the main criteria is the utility, usefulness of the solution. And is it useful and effective enough to solve some actual issues, and hopefully there should be a business value. Our project scope is looking this first two phases. So then simply we have the objectives. First one, design some artifacts, concepts, models, architectures for industrial problems. And the second one, develop and demonstrate these concepts in the industrial cases and evaluate them to, does that work? Or to what extent do they work and the impactful. And the fourth one, of course, disseminate, share the knowledge, share the learnings of this work. So the problems. We have some challenges. I look at factories, manufacturing systems are my core research area in this research time for 3 years' time. We have three domains in manufacturing. One is obviously product, we have to produce and deliver, and the corresponding processes to produce them. And also, of course, the manufacturing systems here representing factories, tools, resources there. So they are quite tightly related with each other. But story does not end there. We have product service system. We have to, especially in wind turbine case, transport them, install and service. So these are also quietly related with supply chains, inbound and outbound, of course, under enterprise strategy. All these domains covered by market dynamics, which are becoming quite important for us because, for example, the demand impact. Unfortunate events in Ukraine, for example, now creating pressure on the demand of wind energy. And there are time to market. We have to deliver our products quite fast. There are disruptive technologies impacting different areas of our operations. And of course, cost pressure and some regulations, especially in the wind industry. There are some weight and size issues that we cannot bend. And most importantly, localization requirements. This is a bit unique. Maybe I can tell a few words. So if you simply sell a couple of turbines and win the project, for example, we won one in New York. If it is $2.5 billion, for example, then the governments jump in and say, wait a second, if we have to pay so much money to a Danish company, you have to make some investments here, create some jobs. So it's, in fact, quite much already complex and difficult supply chains. Wind turbines I worked. So you see here the picture is the Blue Marlin is our upcoming product. It's a 15 megawatt turbine. It's one of the biggest. It will be on offshore. End of this year, we will have first prototype. Why it's the biggest? Because very simple physics rule. The area that wind blade covers is called swept area. If it is bigger, we capture more static power from the wind, so we can create more energy from with the same turbine. So that means turbine performance will increase. Why this is so important also? Why not we put more turbines? Because we don't not actually sell turbines. We go and give cost per megawatt. Whoever gives lower cost per megawatt is likely to win the tender. So if turbines have higher performance, which means they are bigger, then you are most likely win the tender. That's why turbines are getting bigger and bigger and heavier, more complex. This is the molds of that turbine, 115 meters. So these are simple graphs showing how the swept area size goes upwards, rotor diameter, and the weight. This is actually the nacelle weight there is not updated. Nacelle is a simple box on top of these towers. The Blue Marlin nacelle, when it's fully loaded, will be 600 tons, more than 600 tons. And while this is happening, the cost goes down. That creates huge pressure. Full tower of blue marlin reaches 1 megaton. The blades are the lightest components of a turbine. The blue marlin one blade transport tools reach 50 tons. So overall turbine will reach 2 megatons. These are quite a big challenge. So simply, the products are changing. So when they are changing, we have to consider the processes we produce them and deliver them and transport. So when these are changing, also we have to consider our systems to handle these changes. So this is called coordinated or concurrent evolution, or in other words, coevolution. So this doesn't, of course, have to be triggered just by products. It can be just a new technology or new regulation. So long story short, markets are evolving, and this evolution impacts us in terms of coevolution in manufacturing. So that's become the challenge, because we had it actually a long time, we were handling it, because now we cannot, the complexity increasing. We also have other issue, we have shorter life cycles. We have to deliver much bigger, heavier, and much complex turbines faster than ever before. It's not all bad though. We have some opportunities. So we have these dynamic, complex models in products, processes, and systems. But this means, okay, computer screens simply not good enough to deal with this dynamic, complex models, but we have virtual reality that allows us more immersive interfaces. Digital twin is a quite important technology and quite popular, and buzzwords used everywhere. Why it is important? Because given the word, when we say virtual, in the dictionary it sounds opposite of real or digital. But what makes those data and model in the digital platforms or virtual environments is the link between them with their real counterparts. So there is manufacturing data analytics, advanced manufacturing data analytics, also very important, simply because mathematics has no mercy. And the 3D simulations are getting very advanced because they allows us to create these environments more immersively, and allows us to integrate different technologies like digital twin and the virtual reality, and also different methods. So why we need them? Not to kick everyone out from these systems and let them do everything themselves, is actually create new skills. We need them, use them also train new workers. So still, we need to know how these new technologies should be combined and managed successfully to handle the issues which we are facing now and in the future. We need to investigate also these effects of these technological developments and in terms of operational management and business competitiveness. So I want to say a few things about digital twin. That's an old definition made by NASA. There are already quite some critics about this definition, some updates called. So it simply says the digital twin, an integrated simulation, probabilistic simulation, has sensors data and mirroring the life of its corresponding system. So one critics, for example, when we look at this, classifying these models and physical and digital models in terms of data integration, if we simply get data manually from the physical and send the results back from digital manually, it is not a digital twin, just a digital model. If we gather data automatically, but send the results back manually, then it's just a digital shadow. But if we have bidirectional automated data integration, then it's a digital twin. Unfortunately, in literature, many researchers actually just focus on digital shadow or digital models. So in our solutions, we try to achieve this data integration between digital simulations and reality, not directly via manufacturing execution system, but we also test with the IP to prove that it can achieve the link via MES to physical objects. That time I couldn't do it because simply there was not a connected machines in the factories I was working on. So smart factories, title of my research. What is it? This is just one definition. There are many out there. All of them have slight differences, but simply when we look what are the capabilities, smart factories are context-aware systems. They can understand the manufacturing system's problems and develop solutions and implement them. So how we can achieve it? Some say the virtual factory is a way to go there in terms of visualization and data integration, data utilization. But I could even add this, there is also virtual factories capability to different technology integration. Because for smart factories, we need so many technologies. We need artificial intelligence, machine learning, IoT, VR, digital twin, and also different methods. What is virtual factory? When I look at the virtual factory literature, I found so many different models, concepts, frameworks, and the quite old ones. And it goes all the way back 1993, it's mentioned. It's quite old, 30 years old. And one of the recent ones, 20 years ago, the literature defined virtual factory as an integrated simulation model of a factory, considering its subsystems as a whole and support advanced decision capability. So when I map them, we see all research actually look different, distinct perspectives of virtual factories, different technologies, and some are the pilot works or lab works, some were the actual cases. The idea was that why don't we bring these different technologies together and have this solution put in the actual real life case and to explore what kind of usefulness we can capture from this. So we find various needs, gaps from the literature that we can address with this work. I will not go through all of them. But first, we said to answer those, close these gaps, we need to design a concept and based on real life cases and then which can utilize different technologies and especially product, process, and system models in it. And then we want to discover how can we actually develop and implement it, because that was a need, that the guidelines for the actual guys and experts in the industry. And third one, of course, find the enablers and barriers and evaluate it in the industrial purposes and discover the value, if there is any. So we create some questions. First one looking how can we develop this concept and with the state-of-the-art technologies for an industrial case. Second one was extending with digital twin capability and multi-user VR and evaluate it to could it be support industry for handling coevolution. This is quite a generic question. Actually, I could consider it the overall question of all my PhD. And the third question derived from the first two actually during the research. It's shaped and updated. We thought that we are talking so generic things. We need to evaluate in the specific cases. So during this research, we get feedback from industry experts. New product introduction, NPI processes could be quite valuable to evaluate because NPI is, in terms of a change, has the highest magnitude in the manufacturing organization. So you need to change the whole new product, and new processes, and new production systems. And the last one is also a result from all this work. It wasn't intended in the beginning. We find out that there is actually quite few research considering or discussing the conceptual or theoretical background of this concept and solution. Based on what theories and concepts this could be useful. So we thought that it would be nice to also focus. So we break down all questions. I will not go through all of them, not to make you bored more. So first phase. We had 3 phases, and each phase we simply had same processes: design, develop, demonstrate and evaluate, and disseminate what you find out. First phase focused on building the concept and developing it in the industrial case and see where are the values. Second phase, we thought that we need to extend the capabilities, technological capabilities, and with the digital twin and multi-user VR. And the last phase, we tried to put in the specific case and virtual prototyping for NPI. So the first paper addressed some of the gaps we find in the beginning, as I showed before, and the second one, another ones. These are more like practical challenges and gaps. And then we put a more specific evaluation, and the last paper tried to address some needs in terms of theoretical and conceptual foundations. So, about the methodology. So, we follow design science research methodology because, we have two domains mainly. One is application case, which is industry, Vestas. Another one is knowledge base, which is the scientific papers out there. We need to find a problem in industry and design a solution based on existing knowledge and test it and send it back. But let's look how it looks in our context. We have some capabilities, problems, and strategies in Vestas, and we have existing knowledge in the literature, some theories, concepts, and models. So what we did in our cycles, first we found the problem in the industry, captured the requirements, and then we look at the literature, what is existing knowledge there, what are the existing concepts, models, and how can we utilize this knowledge. Then we design a solution based on this. And then, this is also maybe important, we try to find and ground the design decisions, why we design the solution in this way. And fifth step, going back to the application domain in our industry pointer and demonstrating it in actual case. Then the knowledge we gain from these demonstrations, we evaluate our design. And of course, share what we learned with the academia. But also another last and critical one, we try to look back, does this answer the questions we asked in the beginning? So there are 6 processes in design science. We follow these 6 steps for each cycle, each phase. I will not again go all the details, but each phase we simply try to utilize some problems, capabilities, strategies from our industrial partner, and also we try to use existing knowledge in terms of theories, methods, and gaps. So first phase, we follow them, and what we learn in the first phase, we update our objectives and design, and make another evaluation. Based on that, we change our objectives, make case-specific evaluation. So let's look at a bit what we did in solution type. So factories are highly complex systems. But what is even a system in the first hand? A system consists of several essential parts and or subsystems. So each part affects the performance, essential properties of the system, of the whole. But no part have independent impact on the whole. So if you look, for example, my body, if I want to run fast, simply having more longer or stronger legs are not enough. My heart should be strong enough to support for my body to run faster. Even my brain maybe should be strong enough to manage this process. So the parts doesn't have independent impact in the overall performance. That's why a system is not the collection of its parts. A system is the product of the interaction of its parts. So what we deal in here, factory is simply highly complex and evolving systems of actively interacting problems. Traditionally, we deal with this problem by analysis approach, by simply layering down these complex systems in different layouts. For example, in factories, we have Excel sheets studying timelines. We have 2D drawings looking at the 2D layout. Other drawings about just process flows. Simply these start failing more and more because of increasing complexity. That's why we need a synthesis approach as a complementary to this analysis approach. So we designed the concept. We have 2 life cycles. One is a product life cycle and another one is production life cycle. When there is a change in product, process, or systems, we have to go through these life cycles to update our existing system. One side, we have a real factory with some IT infrastructure capturing the data from what's happening actually there, representing our system. Another side, we have really comprehensive PLM solutions representing our product models. So, and in between, we put the virtual factory. There's an integrated simulations representing the factory. But as I said, when we consider them working these domains individually and isolate independently, then it doesn't work well. Because whenever we change the product, we have to go to processes and then the reality. So that's why we aim to linking them in real time. So we try to achieve with virtual factory a dynamic representation. What it means. So in reality, everything is dynamic. If you go to factory, you don't see the things, the layout as in the drawing in the 2D system, or the product CADs standing in some corners. Everything is moving, everything is changing. So that creates one issue. We try to achieve a dynamic representation of actual reality with virtual factories. Another one is open. So every system is open actually, like production lines or factories. They are getting some inputs like tools, resources, labor force, and ideas, and give some outputs. So, but most of our existing IT platforms are not that open. The PLM has its own complex product models, engineering or bill of materials, manufacturing bill of materials. We try to have a solution which is open to other integrations. The holistic, which I mentioned also, looking some specific part independently, solving problem there is not enough, because mostly it creates a chain of reaction. If I change some part of the production, mostly I have to update the delivery system from warehouse, then warehouse, and maybe all the way to supply chain. So here we try to represent the whole system in a solution. Cognitive is a bit tricky word. It's simply easy to make sense. So we have this really complex, detailed engineering models in different platforms, and all specialists in their own area did a great job. But the organizations doesn't work that, people doesn't work independently. That should be, to some extent, easy to understand and comprehend people from different departments. So as a result of this, we also thought that maybe the definition of virtual factory should be updated. So we propose the definition. So virtual factories are not just integrated simulations. Virtual factories are now becoming an immersive virtual environment where we can create digital twins of all factory entities, and we can relate them, create them, simulate them, and I think most importantly, we can manipulate them. So this is the video I developed 4 years ago. First time 3D discrete event simulation. That blue thing moving on there is a CAD model of an actual wind turbine. So when I did it, it was amazing. I thought, okay, if I can put one part of a turbine, so I can, put the actual layout and create actual walls, factories, tools, environment, processes, and link them with different platforms. So I will have a virtual twin of reality. So then we did. We get an actual layout, actual CAD models, and we link them with each other. What you see here actually quite an old, and after a month of fight with legal department, I was allowed to publish. So that's the tip of the iceberg, but I'm sure it will help you to understand what we mean. So simply, we build the factory with different components in different perspectives. Each of data come from different guys. We link them. We try to achieve different unique processes there. Then we simply try to have product, process, and system models integrated with each other. We import data from real manufacturing execution system and actual production. So what you see here is not just a 3D discrete event simulation of a production. All the data for these processes came from factories in real time. So when the production stopped in factory, it doesn't work in the simulation, which has happened. We thought it was an error, but then we find out that it was an actual purpose of our work. Then we can run some data analytics. And most beautiful part, what is the purpose of having such a good exact model? We can manipulate it. While this line is running, I was able to change the location of the operations, and I was able to see the real-time impact of this change in the data analytics part. It's not just 3D fancy bingo. You can go inside with virtual reality, verify, analyze the processes. So whole line, I told the operations in the line were virtual twins, except one. One operation we assigned a VR user. He has to perform the assembly task for the training purposes, but because it was in the virtual factory, we were able to real-time observe his impact of his performance to the production line. So if he does not finish task on time, virtually he will block the line, and our factory manager will get so angry. So at the end, automatically we send the results back to manufacturing execution system. So I will jump to another one, actually. So we made another simulation. One operation in that line, we have to coordinate. I mean, operators have to coordinate in one process, and also one of them has to coordinate with other. David from Denmark, from Portugal, and I was in Denmark. It wasn't me, it's my avatar. We met in one virtual environment. We were hear each other, talk with each other, and we have to perform a process in a much more higher resolution in this multi-user VR simulation. The time clock you see on that wall, it's coming from actual production. It's actually showing the time of an operation just before this one. So simply again, if we do not finish our task on time, we will be virtually blocking the line. So we did not just perform this process, we record our, in this case, proof of concept, our time to finish it. And in that previous line simulation, we utilize our time. We perform to finish this task. Simply, if the trainee, during the training, if the people takes longer time to finish task, So that time will be used in the line simulation, so we could see how will it impact the whole line. So these are all on YouTube, by the way. You can watch all of them. So let's look at the results. First phase, we published a paper focusing on building the virtual factory as a journal paper, and the second phase, we extended it and a bit more extensive work related, because the question was big and broad. Could this support coevolution? And the virtual prototyping, we focused on the specific cases of new product introduction. And the last one, in the theory papers, and we focused a bit conceptual and theoretical foundations here. And the paper actually was updated, after saying in the thesis. It passed a minor revision, hopefully will be the last one. We also introduced, of course, various artifacts. I will not go and try to explain all of them, but we simply try to put there our methods, our procedures we follow during this work, what we learned from the industry, architectures. These could be, of course, a bit specific to Vestas, but it could be extended to different industries. This is, for example, architecture for multi-user virtual reality. And of course, some evaluations and feedbacks from industry experts. So these are just simple graphs I put here, but there are actually quite nice comments to elaborate on this solution, what would it mean for the industry. So lastly, also, we look at the theoretical and conceptual foundations. We elaborate on this, and also we try to extend our solution to virtual enterprise. I will come to that a little bit later. So we say that virtual factory is a systemic way, a systemic approach to build smart factories. What that means, the factories are really not just static systems or IT systems or mechanical systems. They are highly dynamic, evolving, complex socio-technical, socio-economic, and artificial systems. If we isolate these parts of these systems independently, so it will be challenging to handle the change. That's why now with the systemic approach, we can divide the system in different layers, look at the parts in different level of resolutions, while we can see still the impacts of this change in different levels. So simply, systemic approach means that it's just a way to handle a complex system with a global point of view without focusing on some specific details. So it also aims for a better understanding of complexity without simplifying the reality too much. So it's simply focusing the conception and the communication of complexity. So we do not look independent parts and factors when we look in the whole system. We are looking at goals and interaction. And of course, most importantly, we can look at essential properties and emerging properties to handle coevolution. And how we do it? Process rendezvous, we call it. Production and product and production lifecycle processes can meet in virtual factories, so we can see how will it work or not in virtual factory. So by achieving architectural isomorphism between the modules from product, process, and systems. So come back to questions we addressed in the beginning. We try to answer each one of them in different papers. The first one, we try to simply introduce new concept, methodologies, procedures, architecture, and using VR in computer-aided manufacturing. And paper 2, focusing the extension of digital twin and multi-user VR, and evaluating the solution in the coevolution context, also concurrent engineering and time to market. Including also evolution of our artifacts, of course. Paper 3, focusing on demonstrating this virtual prototyping cases and evaluating this specifically for NPI processes, and especially 4 different types of prototyping during the introduction of new prototype. It has really quite interesting feedbacks there, which areas it could be more valuable or what type of simulations could be more valuable for each case. 4th paper, we try to introduce conceptual and theoretical frame and extend the solution to enterprise level, not just limited from factories, which is actually our actual real work with this investors, the operations of outside factory. and of course, elaboration of the solution based on concepts. Future works. What we have, digital twin-based factory, was not just a nice-looking solution in Vestas. The moment actually I finished my PhD a year ago, that Vestas decided to invest in this. We had a quite comprehensive simulation solution, integrated simulations, web-based. So we finalized installation of that solution, and it's live since February, Vestas. So now the integration with different platforms, with the manufacturing execution system, which is Acquiso, and our PLM solutions is going on. So we will hopefully soon be able to create digital twin-based virtual factory models to simulate processes, verify, validate, and hopefully optimize. And extension to virtual enterprise. This is actually now our work that we simply, as soon as we come to the end of the research, we realize that factory is, of course, super critical and important, but especially in an industry like Vestas, the value chain itself, I mean, the same principles force us to consider operations outside of the factory. We simply try to simulate now our supply chain, inbound and outbound, and also specific operations in the transportation, for example, pre-assembly operations in different harbors, and installation of turbines. That's why we also now particularly working on multi-resolution supply chain simulations together with a participant here, Patrick. He's a master's student. We had some solutions. I will also show you about that shortly. Also, we are looking at reconfigurable manufacturing systems with Stefan here as a PhD candidate. With him, he's working in RMS. We are trying to simulate reconfigurable manufacturing systems in virtual factory simulations to verify the solutions in advance. Multi-user VR, another critical thing. You know, like a company like Vestas, we have factories all around the world: China, India, Brazil, America, and so on and so forth. So we have to collaborate a lot. And it's not just now silo working with different people in different departments. It's that different parts of the world. They have to come together, find solutions to these challenges which I mentioned. So multi-user VR can provide us a platform that people can come together, design the factories, simulate them, verify them, and maybe hopefully implement them to reality. So this was the concept which we developed. In the future works, we just extended it to enterprise level and put some simulation operations outside of the factory. And that paper we just submitted to a conference in Euroma, Berlin. It's accepted. Hopefully, it will be presented and online near future. So I want to show a little bit outside of the factories. So we are having projects in different parts of the world. Suddenly, we have to establish a huge assembly site in the harbor of New York. So we have to create a new supply chain. We have to transport things on the harbors, and from the other harbor, have some operations there, and then send them to offshore locations to installation. So this is for demo for the Blue Marlin case. Another critical thing may be this tool, for example. Patrick learned this tool. While he was learning this tool, he was developing this solution. It took just 2 weeks. It's not just because we are genius, we do it so fast. It's because these solutions, these technologies becoming so easy to use, easy to learn, and model the future scenarios. We put the estimations, the parameters. They are not always fixed parameters. Mostly they have huge deviations. So when we bring them from Excel to this kind of models, suddenly we have a quite integrated model and integrating different data across the manufacturing value chain. And we can have a better forecast about the future. Of course, the ultimate parameter in business is the money. So we can put some cost parameters and see the cost of the scenarios which we have in our mind, of course, for different cases. So, in the simulation, we can, of course, look at different data analytics and look at different parts of the operation. But as I mentioned in the beginning, it's not just a part. We can just use the data at the end as a plan to execute, or we can see the bottlenecks in our value chain in the future, so we can consider handling some big issues, failures, and challenges far ahead we are facing them. So if there are so many parameters in the simulation, of course, as I said, they are not just fixed parameters, there are deviations. We can also change the parameters in the simulation and directly see the impact of those changes in the model. This is actually quite useful for quite a comprehensive models which different people from different departments have to work together. So if you have so many parameters and if we try to go for different ideas, it becomes difficult to change each parameter one by one and look at them. We can create different scenarios, and for each scenario we can determine the parameters, and because there are deviations, we can run each scenario a couple of times simultaneously and see the average outcomes of each scenario based on our predefined performance criteria. So that was all, actually. Thank you very much for your attention. I have to say thank you first, Manufacturing Academy of Denmark, Vestas, and Inestec to help us to fund and provide the materials of this research. I'm very much appreciate for this support, and of course, my supervisor, Professor Charles Möller, and Associate Professor Arne Bilberg for their supervision during this research mine. That was it. I appreciate it.
Yeah. Thank you very much. Thank you very much. Very interesting presentation.